Good morning. Today we will start our unit 2, economic operation of power systems. What is economic operation? Power is generated at generating stations, transmitted, distributed, and it reaches to us. So from DISCOM, distribution companies or power companies or generating companies point of view, they tries to minimize their expenditure for a particular revenue. Whatever they are getting revenue from the customers, for that particular revenue, they tries to minimize their expenditure. And the major component of expenditure is fuel cost. It is significant when we are talking about thermal power plants or nuclear. For hydro, input is water, output is power. So water is almost free, but for thermal power plants, coals are not free. The persons working there, their salary, their pensions, etc., all expenditures are recovered from the customers. That contains their expenditure plus their revenue, their profits. So from generating side, they tries to minimize their cost. First we will discuss the characteristic of a unit. Unit means for a thermal power plant, it consists boiler, turbine and generator. So first we will discuss the input output characteristics of a generating unit. Write down. Generator operating cost of a thermal power plant. Thermal power plant. Right here, megawatt mean megawatt max. Basically it is power output here on this axis, power output. And what is input? Fuel cost. So that may be in terms of million calorie per hour, or we can convert in terms of rupees. So directly we can write here fuel cost in rupees per hour. So the relationship between cost incurred for generating various level of power is not linear. We can see it is non-linear. So experimentally we can construct this curve. Say during experiment on a particular unit, you are increasing the load, output power, and you are calculating the fuel input required to generate that particular level of power. So this way you will have certain points you will get, right? After that, using curve fitting techniques, you can have a polynomial like this. What is MW mean? Megawatt mean the minimum limit of that particular unit for generation. Below this, either it is technically not feasible or not economical. If you are going to generate, then it will not be economical. So you have to generate between these limits, and this is the maximum capacity of that particular unit. Unit means boiler, turbine and generator. Set of boiler, turbine, generator means one unit. So we are having this input output relationship for a particular unit. So we at a particular generating station we may have many units, many such units, and all units may not have similar characteristics, they are having different characteristics. So it is a task for you to decide at a particular load demand which unit to be loaded at what extent, so that to get the maximum benefit, minimum expenditure occurred for generating a particular power demand. Clear? So suppose this polynomial after curve fitting we are getting a simple one quadratic. So let us denote that polynomial. What is this output? Cost. Denote it by Ci, I for ith unit, cost of ith unit equal to, what is the equation of a quadratic polynomial? Like that. Okay, write half ai square pgi plus bi pg I plus ci, or better c is here, di, right here di, equation 1, where square, where pgi is the power output of ith unit. So this is variable, like you said half ax square plus bx plus c, this is a polynomial of order 2, quadratic polynomial, right? So there x is variable, so by varying x you get different f. So here our function is cost and it depends on which variable? pgi. With varying pgi we are getting different ci. So I denotes a particular unit. So depending upon the number of generating units at a particular power plant, we can have different such relationships, means different coefficients ai, bi and di for a particular unit, right? So differentiate it. So first derivative will be dci upon what is variable? pgi. This will be equal to a pgi plus bi. This is slope of this curve, right? First derivative. This is known as incremental fuel cost. Right here, this is incremental fuel cost. So different units will have different ICIs, right? ICs, incremental fuel cost. So for a particular demand, suppose PD, here we will denote PD let us denote the total demand on the bus bar, means on the generating station having k number of units, say k number of units is D. PD is total demand, power demand which you have to satisfy. So and each unit is having its maximum, right here P max I. What is that? Capacity of ith plant. So total number of units, let us say number of units are k. So summation of all the capacities, summation of capacities of all the units should be equal or greater than PD. Clear? At least this should be. If all the units are fully loaded, so at least we should be able to fulfill all the demands, power demands on the station, right? Second, we can observe that all the units should be loaded within its limits. It should not violate the limit. So PGI, loading at ith unit, should be within PGI mean PGI, fine. So once we are talking about capacity, so in that case this is valid, fine. Actually we are not going to load all the units at its maximum capacity due to economic reason. We have seen the curve, right? So we have to load in between these limits. So suppose each unit is loaded at PGI. Suppose unit 1 is loaded at PG1, unit 2 PG2 and unit K PGK. Then we can write I equal to 1 to K PGI should be equal to PD. What is PD? Total active power demand. Total active power demand. So generation from all the working units should be equal to the demand. So this is a constraint. And for economic operation, our objective will be to minimize the cost. But cost depends on PGI. Equation 1, just see it. Cost depends on PGI. So we can define an objective function, say Ci. C equal to summation of Ci. Ci is cost of ith unit, or you can write it is a function of PGI, right? Ci is function of PGI. Say equation 1. How many units are there? K. So this will be total cost of generating C1 plus C2 plus C3 plus Ck. Total cost. These are total cost for generating Pg1 plus Pg2 plus Pg3 plus Pgk, so on, right? So our objective is to minimize this objective function subjected to, right here, subject to what is constant? We can write same thing, I equal to 1 to K minus PD equal to 0. So this is an optimization problem. How many of you are aware of optimization problem, optimization techniques? No one? Recall your class 12 concept when you are having a simple function in x, single variable fx. You are required to get the maxima or minima of that. That is also optimization. Simple optimization problem with single variable without any constraints. There are no constraints were there. Recall, suppose you are having one function fx in variable x. You want to get the value of unknown x at which f will be maximum or minimum, that is optimum. So there you used to write the necessary condition, write f dash x equate 0 and get the critical points, stationary points. So this was necessary condition. Then again take double derivative of this and check the value at critical points. If it is positive, then minima is there. If it is negative, then maxima is there, right? So that is also optimization. The objective is to get the optimal value of f. So that was procedure. Suppose somewhere it is given x is equal greater than 0. It means it is constant. So you have to take x corresponding to positive only. You have not to take negative x. It means this is constraint problem, optimization with constraints. So although if you are getting some x negative, you will discard that because you are having one constraint here. So our problem is, how many variables are there? Not one. K. Pg1 is a variable. You don't know the value of Pg1. You have to calculate the optimal value, to get the minimum cost, because cost of each unit depends on the generation of that particular unit. Suppose for unit 1, C1 will be depending on Pg1, you don't know the value of Pg1. Similarly, C2 will be depending on Pg2, Ck will be depending on Pgk. So you have to find similar to that this variable x, but here we are having an optimization problem with multivariable optimization problem. So right here, what is your objective? Maximize or minimize? You will minimize cost, right? Minimize, okay, minimize C subject to this. So this is an optimization problem of how many variables? K variables. And how many constants? One constant, right? So this optimization techniques falls under the category of multivariable optimization with equality constants, right? Sometimes we may have inequality constants. So different solvers are there, different optimization techniques are there for different types of problem. So for our problem, which is multivariable optimization with equality constants, generally two techniques are used. One is substitution method, where these are substituted here, and most common is Lagrange method. Have you heard the name Lagrange multiplier method? Yeah. So this is also for a particular classical optimization problem. So we will proceed with Lagrange multiplier method. So first we used to make a Lagrange function denoted by L. What is that? That is objective function plus summation of j is equal to 1 to m, where m is number of constants lambda j, and suppose this is gj. J is 1, so you can write here directly g is also a function of pgi. So 1 only. Where pgi? Yes. Pgi minus Pd equal to 0. So this is another function known as constant function, and here we are having just one constant, so it is a very simple. If we are having two constants or m number of constants, so we can proceed using the similar procedure. So the first step for solving such type of problem using Lagrange method is make Lagrange function. Say this is L. Obviously this will be function of Pgi is equal to same function Ci, C, that is Ci Pgi I equal to 1 to k plus or minus, just introduce one constant known as Lagrange multiplier. You can take plus or minus, doesn't matter. You can multiply both sides with minus, right? So this will be 0, or Pd minus this will be 0. That can adjust the sign of lambda. Write this one. This will be summation I equal to 1 to k Pgi minus Pd, or Pd minus this. So you can put here minus or plus, doesn't matter. This is our new function known as Lagrange function. Clear? So what we have done till now? Just we have introduced one new function known as Lagrange function, consisting of our objective function or plus or minus some constant known as Lagrange multiplier times the constant. Suppose we are having two constants, so we can write lambda 1 this first constant plus or minus lambda 2 second constant, and so on, right? So similar to that particular necessary condition for fx, and you have to optimize, you are taking first derivative equal to 0, that is necessary condition. from where you will get the critical points where you are having doubt whether optimal is there or not. Later you have to check, but you can guess at least these are the points where chances are there for maxima or minima or point of inflection also, right? You know it. So necessary condition for this will be del L upon del PGI equal to 0. First partial derivative of this equal to 0. Similar to that, fx is equal to 0. You have to solve it. So based on that you will get the values of PGI. What are your variables? PGI. I is equal to 1 to k. So you will get values of PGI. So at those values you may get optimal value of the objective function. So first take del L upon del PGI. What is your del L? This one. So this will be nothing but take first derivative. So PGI is there, means this is function of this, otherwise it will be 0. So what is this? You can write del Ci upon del PGI, fine, minus lambda, this is constant. What about this? What about this? This is Pg1, Pg2, Pg3 plus up to Pgk. So take any value of I, suppose Pg1. So this will be Pg1 plus Pg2 independent of Pg1, Pg3 independent of Pg1 up to Pgk independent of Pg1. So you will get 1. Or take 2, I equal to 2. So Pg1 will be independent of Pg2, so 0. Pg2 will depend, that is 1 plus 0, 0, 0. Take any value of I, you will get here 1. So write here 1 minus, this is constant independent of PGI. It doesn't matter for a demand from which unit how much you are generating. It is independent of that, right? So here what we will write? 0 equal to 0. So this way further Ci is C1 or C2 or C3. So okay, del C basically our function is this whole, right? Fine. So this is C1 plus C2 plus C3 and C1 is depending on Pg1, C2 is depending on independent of other Pgs. Suppose C1 is depending only on Pg1, independent of Pg2, Pg3, Pg4, right? So Ci is only depending on Pgi. It is independent of Pgi plus 1 or Pgi minus 1, right? Suppose I is 3. So C3 is depending on Pg3. It is independent of Pg1, Pg2 or Pg4 up to Pgk, right? So partial derivative can further be written as first derivative. This right here dCi upon del Ci upon del Pgi can be written as dCi upon dPgi. Can we write this? So substitute this here and we can write dCi upon dPgi equal to lambda. What is dCi upon dPgi? Equation 2, incremental fuel cost, that is IC. So we can write that is equal to lambda. So put I equal to 1, dC1 upon dPg1 equal to lambda, put I equal to 2. So we may write dC1 upon dPg1 equal to dC2 upon dPg2 equal to so on dCk upon dPgk equal to lambda. Very important equation, equation number say 3. This is known as coordination equations, right here coordination equations. What we can observe from equation 3? For optimal load dispatch, the incremental fuel cost of each unit should be equal, and that will be lambda, Lagrange multiplier, also ICI, incremental fuel cost of that particular unit. So we are having different input output characteristics of several units. So one point we will get where slope of that curve is equal for different outputs, is not it? See that curve, input output characteristic. So suppose we are having 2 units. For 2 units we will get 2 points on each curve, 1 point on each curve where slopes are parallel, is not it? Slopes are parallel means m of that curve is equal to m slope of that curve for that particular PG and that particular PG. These 2 PG will be different, may or may not be same, but we will get, suppose lambda is something, suppose 1.5. So for particular polynomial you will get one slope corresponding to 1.5, you will get 1 point, corresponding to that point you will get 1 PG, fine, right here. For second unit you are having different input output characteristics. So for lambda is equal to 1.5 you will get 1 point on that curve, is not it? Corresponding to that point you will get 1 PG. So these 2 PGs are suspected to be optimal. Till now we have just taken necessary condition for solving that classical simple problem fx. So f dash x is equal to 0, it doesn't confirms that you are getting minimum of that particular critical points. Next check is sufficient condition, that is double derivative of that there for single variable optimization problem. But for this sufficient condition is not in the scope of your UG program. After UG you might be reading this optimization technique, and there during the study you will get the details of that. So just remember that this is not sufficient, but it has been checked, and those checks are, okay, I will write here briefly, but no need to worry if you are not understanding, just have an idea. You have to solve one polynomial, determinantal polynomial, and you have to check the roots. So those determinantal polynomials will be, say, L11 minus z, L12, L1k, L21, L22 minus z. Diagonal elements will have minus z in addition, and so on. L2k, Lk1, Lk2, Lkk minus z, diagonal elements. G11, G12, G1n, here n is k, and similarly G21, G22, G2k. Suppose total number of constants are m, so you will get m1, Gm2, Gmk. Take transpose of this, so G11, G12, up to here G1k, G22, G2k, and so on, Gm1, Gm2, Gmk. Remaining positions will be filled with 0, 0, 0, 0, 0, 0, equal to 0. This is a determinantal equation of a polynomial in Z. So solve this for all Z. So all roots of this polynomial should be of same sign, either positive or negative. If all the roots are positive, it means corresponding to those critical points obtained through necessary condition we will get. If maximum, then we will get minimum. If negative, then we will get, if all roots are positive, then we will get minima. If all roots are in other way, then we will get maximum point, right? So, but here you are having just one constant, so you write this first row only, this one G11, G12. What is this L and G? And here we will get this only. So up to here we will get for one constant. So for m constant in general we have written this. So what is L11? L11 is nothing but del 2L upon del Pg1. Suppose del Lij, better write Ij, general term. So del Pgi, del Pg, G. Pgi are our variables. Suppose x1, x2, so we will write del x1, del x2 like that. Here we are having our variables in terms of Pgi. So Pg1, del Pg2, right. What about G? You may write Gij is nothing but del Gi upon del Pg, G. Suppose G11. So G1 we are having just one constant, so we will get one row only. No need to calculate 2 or 3 like that. So G1 is that G, del Pg, J. So del Pg1, del Pg2 like that, corresponding to this. Suppose you are trying to calculate G12. So G12 will be I is 1, J is 2. So this will be del G1 upon del Pg2 and so on. No need to worry, just to have an idea that what is sufficient condition for our problem. So this way it has been checked and confirmed that that particular equation, equation number 3, is coordination equation, and corresponding to that we will get the optimal loading at different generating units.
So how will we define the value of lambda?
Okay, lambda is any constant and it is solved iteratively. You have to take one iteration for that. We will proceed later. So at least you have an idea. See, you are having polynomial, so you will get one y-intercept. So that lambda should be at least equal or greater than the bigger intercept of all units. You are having different y-intercepts. You know y-intercept? Right. So that lambda should be, to have an idea, but it is not known that what should be that lambda. That is our objective, to find that particular lambda for which incremental cost, incremental fuel cost of all the units are equal. That is a task. So later we will discuss that, how to get that. First try to understand the concept, on what basis we are going to find that optimal condition and that optimal loading on the different units, right. So we are having one equation, coordination equation, which says that, which states that the incremental fuel cost of all units should be equal for optimal loading, for economic dispatch. Clear? Any other question apart from how to get the value of lambda? No? So next write the steps for solving. So we are going to solve which equation? Equation 3 and power balance equation, that is constant. What is that? Equation number 2. So keeping these two equations in mind, that is total generated power should be equal to total demand, that is power balance equation. One thing you have to keep in mind, total generations from all the units should be equal to total demand on a station, and this demand is not fixed, it varies. So you have to calculate, you have to fulfill all the demands required from morning till evening, day, month, years, like that. So for that different task is there, load forecasting, but means you are having knowledge of load for a particular day, hour of day, day of week, right, week of month, month of year, like that. It is known to you that at what point what is the demand, but keep in mind that demand is not fixed. So that demand will be fulfilled by all the generating units by varying the PGIs. So for fulfilling a particular PD, a set of optimal loadings on all units will be obtained using these relations. Coordination equation and power balance equation. When load varies, so corresponding to that particular PD, next new one, PD2 suppose, you will get different set of loadings on all units corresponding to economic dispatch. Understand? We will see step by step. So first write the steps when PD is known, demand is known, and to fulfill that particular demand you have to find the different loadings on different units. Understand? So step 1, very good question, how to get value of lambda. So first step is assume initial value of what? Any guess? Lambda. Initial value of lambda. Say IC is equal to IC0. Initial assumed value. What is lambda? IC. Incremental fuel cost. Equation 2. Just see it. So you have assumed any value of lambda. Next, corresponding to that lambda, that assumed value. In bracket you may write lambda, assumed value of lambda should be greater than the largest intercept of various units. You know intercept, y intercept, right? See equation 1, di. What is that di? Intercept, right? No, not equation 1. What is equation 2? What is equation 2? So their intercept will be bi. Okay, bi. That is intercept. Intercept of IC. Intercept of IC. So IC is represented by equation 2, not equation 1, right? So intercept corresponding to IC. We are assuming the value of IC. So the initial value of IC will be greater than the intercept of IC equations. Equation number 2. Clear? Next, corresponding to that assumed lambda, lambda 0, whatever it is, solve coordination equation, equation number 3. So there now lambda is known, whatever you have assumed that is known now. Corresponding to that lambda, you will solve how many equations are there in coordination equations? K equations are there. So K equations are there, K unknowns are there. What are unknowns? Pg1, Pg2, Pgk. So you will solve, right? K equations, K unknowns, you will get K values of Pgi. Pg1, Pg2, Pg3 is known now, are known now, right? So once these values are known, you have to check, sum up it, whether you are generating more or less. Is it not necessary that you will get always optimal guess?